Welcome to this very quick video on total internal reflection and the critical angle. We're going to start with total internal reflection. Now you may have seen these objects on the right hand side. These are fiber optic cables. They're quite amazing looking things. They're used in toys and in communications. And we're going to try and understand a little bit about how they work. They're interesting because they're very flexible. You can see the one on the bottom there is wrapped around in a circle, and light is still able to travel down it. And they're also very efficient. They are very bright and are able to send light signals a very long way. Now, if we think about the process by which light is sent from one end of a fiber optic cable to the other, that is due to something called total internal reflection. And you can see the diagram there. We simply have the light reflecting off each side of the cable as it travels from A to B. So we can trace this nice direct path from side to side to side as it goes from its source to its destination. As you can see there, none of the light passes through the material. It only passes within the material. So we say it's internal, and it's entirely reflected at each point. And so this is why we call it total internal reflection. Now, in order for this to happen, this can only happen when we're going from an optically dense material, say for example like glass, into an optically less dense material like air. And that's one of the conditions that's required for total internal reflection to occur. Now, a slightly more kind of mathematical one is to do with the angles that we need to use, and that's what we're going to discuss here. So when we want total internal reflection to occur, we have to be very careful with our angle of incidence. We are able to identify an angle called the critical angle. And the critical angle is an important angle in total internal reflection. When the angle of incidence is less than the critical angle, then what we notice is the usual effect of some light being reflected and some light being refracted. Now it's important here, as I've said before, that we're going from an optically dense, so a large N, to an optically less dense material, so low N. And actually, for now, we will assume we are going, say, from glass or water to air. The reason we can tell that is because in this image on the right hand side, you can see the light being refracted away from the normal as it passes from material to material. And that means it is speeding up, and therefore it's going to an optically less dense material. For this critical angle, angles lower than the critical angle will get both reflection and refraction. However, when the incident angle equals the critical angle, the angle of refraction is exactly 90 degrees. And you can see my light traveling to the boundary and meeting the boundary and traveling along that boundary. In other words, we are perpendicular to normal. The angle of refraction is 90 degrees. Now, missing from this picture is another reflected ray. There will be also a little bit reflected here as well, but the emphasis here is on that refracted ray being at 90 degrees to the normal. We've thought about less than the critical angle. We've thought about equal to the critical angle. Well, we now need to think about greater than the critical angle. At this point, the light is no longer refracted, and the only thing that happens is this reflection, i.e. the light does not leave the material, it does not leave the medium, it stays within there, and it is internal. It is totally internally reflected. So this is the phenomenon that we observed for the fiber optic cable on the previous slide. So identifying the critical angle, if we want to cause that light to bounce from side to side, we must shine it in at an angle greater than C, the critical angle. Now, knowing C is very important, one, so that we can achieve total internal reflection, but also so that we can actually calculate the refractive index of the first material. As I said before, we're saying we're going from a material of refractive index N into air in this case. And that's valid for this equation that I'm showing you on the screen right now. N is equal to 1 divided by sine of C. Now C here is the critical angle for the material with a refractive index N. And so you can see here that actually every material is going to have its own unique critical angle, because every material has its own unique value of n. And you'll notice there that if we've got a large angle, sine is going to be larger, 1 over sine is therefore going to be smaller. And so we can directly link the critical angle to the refractive index in the material. Again, the caveat here being that we can only use this equation when we are going from material of refractive index n into air. If we're not going into air, then the equation does not become valid. However, at GCSE, you wouldn't be expected to apply this. Thanks for watching, and as ever, please do ask me if you've got any questions.